Hello and welcome back to Calculus 1. The next section is 2.5 limits at infinity. So the title says that now we are looking at infinities, which means that x should approach positive or negative infinity. So limit x approaches positive or negative infinity. And we will be looking for finite value. And we'll see the two different applications, because you can also end up with infinity as the answer. So if you end up with a finite value, it will mean something. If you end up with infinities, then it will mean something else. Before we dig into the application, let's take a look at the concept first. So here's our good old limit of 1 over x as x goes to infinity. So it is extremely easy to see on the chart, on a graph, sorry. When you have a graph, you will be going towards positive infinity and observing what the y value of the point is doing. What is it doing? It's going down, and it's going to be what? 0. Very good. So this is how we are going to positive infinity. You can start somewhere on the x-axis and approach positive infinity. So as you are approaching positive infinity, these dots, right, the values on the function and the sense of the y coordinate are going to 0. The next example would be limit x approaches negative infinity for, let's say, e to the x. We will graph e to the x, which goes through 0. Goes through 1 on the y-axis. And what's happening as you are approaching negative infinity? We are getting 0 again. The next question, limit x approaches positive infinity for square root of x. What are we going to get? Look at the graph. We are getting positive infinity, because as the x value approaches positive infinity, the y value is also rising forever, so it goes to positive infinity as well. So if you have this kind of behavior that there is an arrow shooting up, that's going to be positive infinity. So also I can ask for e to the x. Now I'm going to go back and say limit x approaches positive infinity for e to the x, and the answer is positive infinity. Very good. So these guys are going to be this easy. You look at the graph, if you can graph the problem, and you solve it quickly. Now, certain problems, which is when you have the polynomials floating around, you can solve those analytically by using algebra, right? So let's say you have the limit x goes to infinity for x cubed minus 3x plus 5 divided by 4x cubed minus 2x squared plus 1. So we can also solve these types of limits at infinity when you have a polynomial divided by polynomial. The fastest way to deal with this is to locate a term that has the highest exponent overall. You have altogether 6 terms there. And you see that the highest exponent is x cubed. You are going to use the highest exponent to divide every single term in the problem. So I'm going to write over x cubed, over x cubed, over x cubed, everywhere. And then we are going to use algebra to simplify this. It will look worse, but it will actually help. So x cubed divided by x cubed is 1 minus, and then you have 3 over x squared, and then you have 5 over x cubed. In denominator, x cubes cancel, you just have a 4 minus 2 over x, and then finally plus 1 over x cubed. Now I claim this is much better, and it is. So how is this better? Perfect. You notice these structures that look like a value divided by x to some exponent. Let's just think about this first. Just 1 over x. Division means divide to make things smaller. You are dividing one paper in this many units. The result for the whole thing is the size of the piece that is left in your hand. That's the physical thing. So if I am dividing this by 2, I am simply ripping this in half, and the result is a half. Observe that as the 1 over x now is 1/2, it represents this much. If I rip half in half, what do I get? A quarter. Note that the result became smaller as this number went up. And then I divide a quarter in half, and then what do I have? 1/8. So the denominator is again larger. The result for the whole thing is a smaller value. And then here is the 16th, and the 32, and the 64, and then 1 over 28. The original paper has 128 pieces like this all together to create the original paper, right? 256, and so on. 512 of these. I love it. So, as this number grows, the overall procedure, overall result becomes smaller. When I divided 512, right, this is 1 over 512. When I go further, right, to 1024, so what is going to happen as that denominator? What's going to happen with the result as the denominator goes to infinity? It becomes 0. It becomes 0 because as long as I have a concrete number, I will have something to hold. Eventually, I will need the, what do you call it, the tweezers and stuff, right, that you use in labs. 2048 right here. So it's getting smaller and smaller and smaller. So if this goes to infinity, with this being a number, the whole thing goes to 0. So this guy goes to 0. This guy goes to 0. All of these go to 0, and you are left with 1/4 as the answer. So that is the answer to the limit. So by the argument that I just showed you, that the limit, maybe I should write this in red, that the limit of c over x to the p as x goes to infinity is equal to 0 for positive p. The result up there is 1/4. So this is the method to solve these problems as you go along. So when you get the division of polynomials or something similar to it, you can do it this way. Now, usually I say this in class, I don't write it, and then I just wait to see on the exam who paid attention or who watched the stream, because you will catch it again, me saying the same thing. The problem with this polynomial can be solved if you have a sine or cosine on top, because sine and cosine are bounded by 1. So they don't actually contribute to the limit at all. The most sine and cosine can be is 1. So all of this holds if you have a sines and cosines floating around, which is a cool thing.
So it's still 1/4, say in sine.
Yeah, if this was if instead of this polynomial here, you had the cosine x divided by this. Cosine x is bounded by 1, so technically it's just 1 divided by this. I know, it's awesome. It's all the same. You will for the homework, and then you will ask a question if you get confused, and I will explain it. All right, and now finally, drum roll, we need to define the horizontal asymptote. So, if the limit x goes to plus or minus infinity of f of x is equal to L, then we have horizontal asymptote at y equals L. If limit x goes to plus or minus infinity of f of x turns out to be plus or minus infinity, we have end behavior of the function. Now, in terms of end behavior, functions generally have this, or that, right? One of these. So this over here clearly is limit as x goes to positive infinity is positive infinity, because x goes to positive infinity and y goes to positive infinity. So that's the end behavior. This one is the limit of f of x is negative infinity as x goes to positive infinity. Or the ones on the left, one on the bottom says the limit x goes to negative infinity is giving you negative infinity, and this one is limit x goes to negative infinity to give you positive infinity. So if the arrow goes up, the answer is positive infinity. If the arrow is going down, it's negative infinity. If it's on the right, it goes to positive, x goes to positive infinity, and to the left. Just use common sense to sort them out. Now you see both of these at work for e to the x example I had before. Both of these definitions. As x went to negative infinity, I got the finite number, which says that there is a horizontal asymptote at that number, which was y equal to 0. Horizontal asymptote, all lines that are horizontal lines have an equation y equals to a number. As I went to positive infinity for e to the x, we got the positive infinity, and that's that behavior from the chart. So these are the rest of the concepts from your pre-calculus class that were defined, but now we are redefining those concepts through use of a limit to be able to do much broader spectrum of problems. So again, when you take the limit as x goes to infinity, you are either going to get a number or an infinity. If you get a number, you have horizontal asymptote. If you're getting infinity, you are getting the end behavior. So consider function f of x equals to 3x squared plus 1 divided by x minus 5. Do we have horizontal asymptote there? Go on. Crank the limit, see. Where's the horizontal asymptote?
There is none.
There is none. Very good.
That's what I thought.
So we are going to simply do the limit x goes to infinity of 3x squared plus 1 divided by x minus 5 and divide by x squared. So these are the things, guys, that you have to learn. This is your calculus portion. Limit x goes to infinity. We have 3 plus 1 over x squared divided by 1 over x minus 5 over x squared. Now observe that denominator completely goes to 0. So you get 3 over 0, and that's going to be a type of infinity. So no horizontal asymptote at all. But there is something else. Does anyone remember a third type of the asymptote? Slant asymptote. Very good. So we do have a slant asymptote. Slant asymptote is y equals mx plus b asymptote. And it only occurs when you have these polynomials. So when the degree in the numerator is by 1 larger than the highest degree in the denominator. In that case, you can do long division of polynomials to find the equation of the slant asymptote. So in this particular case, I will take x minus 5 and divide that into 3x squared plus 0x plus 1. I use the placeholder on x. And then just do this division real quick to come up with the equation. X goes into 3x squared 3x times. Multiply back, we get 3x squared minus 15x. And when we subtract, we get 15x plus 1. X goes into 15x plus 15 times. You don't have to go further and calculate any kind of remainders and stuff because you already have your mx plus b on the top. So slant asymptote at y equals 3x plus 15. So that's the only place when they occur, and you cannot have a slant asymptote and the horizontal asymptote at the same time. And it only occurs when the degree on top is by 1 bigger than the degree on the bottom in denominator. Yes.
I know I cancel out just with that rule. I understand that 1 over x is 0.
But then this one is 0, right?
And then the top one too.
Yes. So I have 3 over 0. Right?
Yeah.
Cool. So I'm just going to look for a little bit spicier example. Here is a wonderful example for you guys to practice. 42. I would say a medium spice dish. F of x is equal to square root of x squared plus 1 divided by 2x plus 1. The answer is clearly a half, but you can figure it out. I ruined it. Yeah. What are we dividing by? What are we dividing by?
X squared.
X plus square root of 1 over 2x plus
X. The highest exponent is x because root of x squared is x. So we are looking at the limit x approaches infinity, and we are going to divide 2x over x plus 1 over x, and then the square root of x squared plus 1 also divided by x. So what happens now? This is one of the algebraic tricks that you don't see too often, so that's probably why you're not doing so well here. When this x goes underneath the square root, it becomes the square x squared. Right? Of course, makes sense. Math. That's what you love about it. Great. So, guys, if you have a square root of 3x squared, you get to kick x squared out, and it becomes x root 3, right?
Yeah.
Well, stuff it back in. What do you get?
X squared.
Exactly. So, when the value undergoes square root, it picks up a square. If it undergoes x cubed, it picks up a cube. Right? If it escapes, you're losing those exponents. If you go stuff it back in, it gains the exponents. So what do we get? These guys cancel to 1. So this will be a 0. This will be a 0. So we have 1 divided by 2, which is 1/2. All right, let's do one more of these because you love it so much. Next one, 43, good enough. So figure out the limit as x goes to infinity of cube root of x to the 6 plus 8 divided by 4x squared plus the square root of 3x to the 4th plus 1.
Consider the years. Consider the years of my training, yes, right? I mean, apart from your training in wrestling, I mean, just weight-wise, there has to be something. I'm trying to connect my phone to Wi-Fi right now. Of course I do. Yeah. But it's x squared divided by x squared is 1. Yeah. 1, 1. So 1 plus 2. You get negative. No, negative. We're thinking x squared. Yeah. Even a value. Oh, that's for vertical. Your vertical asymptote is the negative one. Your practicing horizontal. Your exam is going to say find all asymptotes. You will have that's that as well. So there will be this procedure for horizontal. You will do that, and then you will run x approaches negative 1. Show that that's the vertical asymptote, and you will also have to stay. You will know Slant decimal. I got the one that take a look with the highest exponent in the entire problem. So square root of x squared is x. So the highest exponent on the numerator is x. And the denominator just has 2x. So again, 43. What's the highest exponent? Oh no, you're right. It is. Yeah, it does. Unless that's a 9 in your problem. But the problem is so far away. And I love the rest. Yeah. You're going to divide by x squared. What? You're going to divide by x squared. No, why? Because 3 x squared is the.
So you all figured out that you have to divide by x squared, right? Yeah. Because that is the highest exponent you have in the problem 43. Cube root of x to the 6 is x squared. Square root of x to the 4th is x squared. And you have also x squared on its own. So you're dividing everywhere by x squared, and then when you undergo the roots, they will pick up exponents. Yeah. They will cancel. These are carefully crafted problems, so they work out nice. Just want to check if that's 3 or 9. Hey, it's 3. Now you got to rationalize that. You gotta rationalize that problem. Yeah. Such is life. Yeah. Rough is coming.
Why is it just that board? So my I understand. I'll say divide by. I also I'm hungry, man. Dude, I don't think I'm making a Wednesday. No, you walk in on idle time. Yeah, right? So it's basically nothing. No lag, no lag. Back edge is full of professors. Nah, I'm good. I got my nuts. I got one over here. Oh, sorry.
Okay. Let's solve this problem and then hit the brake. The highest exponent here is x squared because cube root of x to the 6 is x squared, square root of x to the 4 is x squared, and you have x squared, so it's x squared everywhere. We divide by x squared. And then we put that x squared inside each of the roots, which means the exponents are going to change. So now we have a square root of x to the 6 divided by x to the 6 plus 8 over x to the 6. These guys will cancel, so it's just 4 plus. Oh, that's a cube root there. And then we have a square root of 3x to the 4 over x to the 4 plus 1 over x to the 4. And these guys will cancel and these guys will go to 0. So what I have is cube root of 1 divided by 4 plus square root of 3. The answer is 1 over 4 root 3. And then we should rationalize this because there is a square root of 3 in the denominator. So 1 over 4 plus root 3 times 4 minus root 3 and 4 minus root 3. So it's 4 minus root 3 divided by, that's a 16 minus 3, 13. And there it is. Now you can get the decimal for this, but no one cares. That's the answer.
Alright, how do the x is 6?
It's a cube root, right?
Yeah.
So 2 times 3 is 6. It's the same. Okay, let's try to use the algebraic rule for. So we have the rule that says the square root of a over b is the square root of a over square root of b. And if this is any exponent, that holds as well.
Okay.
So now, if I have, let's say, an x value, and then another x in front, it's going to go in as x cubed, because it was a cube root.
Oh, yeah. Okay.
So it becomes cube root of x to the 4th in that case. Because x that was there times x cubed that just came in becomes x to the 4th. So undergoing. Now you can do that because of this formula here. You can do that in denominator as well. Good. Let me see that I just hit all the points. So end behavior, I already talked about that, and yep, sorry to disappoint, that's it. So let's hit the break, and then after that, in a few minutes, we're going to do continuity 2.6.